off with chapter 8, special counting sequences. The first thing we are going to look at are called Catalan numbers. Catalan numbers. Okay, and what is a Catalan number? For n greater than or equal to 1, for n greater than or equal to 1, actually you can define it for 0. N greater than or equal to 0, define the Catalan number Cn is equal to 1 over n plus 1 of 2n choose n, right? And so what does this sequence look like? N Cn 0, 1, 2, 3, 4, 5, and dot dot dot. For 0 to 0 is 1, 1 or n is equal to 1, so 1 over n is 0, so 1 over 1, all this is 1. For n is equal to 1, it is 2 choose 1, which is 2 divided by 2, so that is also 1. 4 choose 2 is 6, divided by 3 is 2. 6 choose 3 is 6 into 5 into 4. 5 4s are 20. 20 divided by 4, so that's 5. You can check that for 14, for 4 it's 14, and for 5 it's 42, and so on. And if you have looked at the notes of section 7.6, the number of triangular divisions of an n plus 1 gon, in section 7.6, we saw number of triangular divisions of an of a convex n plus 1 gon was equal to 1 over n, 2n minus 2, choose n minus 1, which is actually exactly equal to Cn minus 1. Right? All right. So we have some motivation for why we care about these Catalan numbers. For example, lemma. Well, Catalan numbers are nice. They're exactly of the form 1 over n, n plus 1, this thing. But there's another way to write these. Cn is equal to 2n choose n minus 2n choose n plus 1, n minus 1, plus 1, minus 1, whatever, doesn't matter. And I'm going to choose n minus 1. Proof is relatively simple. Proof, I know that I want to show that 1 over n plus 1 times 2n choose n is equal to Cn. Let us look at so therefore want to show 1 over n plus 1 2n choose n is equal to 2n choose n minus 2n choose n minus 1. Moving terms to similar side, therefore 2n choose n minus 1 is equal to 2n choose n minus 1 over n plus 1 2n choose n is equal to, well, pulling out 2n choose n, I get 2n factorial over n factorial into n factorial into 1 minus 1 over n plus 1, which is equal to 2n factorial over n factorial times n factorial times n times n plus 1, n over n plus 1. I'll cancel this n with n here, and so this is 2n factorial over n minus 1 factorial times n plus 1 factorial, and that checks out, right? So that is my lemma, that they are exactly equal to 2n choose n minus 2n choose n minus 1. So now we have seen that, oh, you can interpret Cn as number of ways of dividing n gone. But let us look at another interpretation of Cn. Another interpretation interpretation of Cn. So for n greater than or equal to 0, consider the sequence, consider a permutation, a1, a2, a to n of the set of the multiset n times 1 and n times -1. Okay, and for 0 smaller than or equal to I smaller than or equal to 2n, let Si is equal to the partial sum is equal to a1 plus a2 plus ... plus ai, where s of 0 is equal to 0, with s of 0 is equal to 0. Okay, so great. If you want to look at an example, take example n is equal to 3. Let me take the partial, take the sequence 1, -1, -1, 1, -1, 1, right? Then Si are for 0 it is 0, for 1 it is 1, for 2 it is 0, for 3 it is -1, 4 gives you 0, 5 gives you -1, and 6 gives you 0 again. Okay. Oops. So that is my partial sum sequence. If you'll notice, s of 0 as well as s of 2n are always going to be 0, because there are exactly equal number of ones and -1s. Okay, so the problem now we are going to look at is problem. Let Hn be the number of permutation sequences that have all partial sums non-negative. That have all partial sums non-negative. Okay, permutations of the set that I'm looking at, which is the multi-set n times 1 and n times -1. Okay, and I want to find a formula for this. Okay, so let me do this. Let me draw an image of this so that it will be slightly helpful for you to visualize it. Okay, so in terms of an image, this sequence looks like 1, 2, 3, 4, 5, 6, 1, -1, starts at 0, goes to 1, then goes to 0, goes to -1, goes to 0, goes to -1, and then goes to 0 again. So my drawing's not super great as usual, but you get how the sequence looks, right? Let me do a better job. 2, 3, 4, 5, 6. Okay, whatever. Okay, so that is how we are going to visualize this sequence, and we can visualize other sequences also by their partial sum diagram per se. Okay, so let us look at how many sequences do I have. So n sequences, and hn. So for n is equal to 0, there is no sequence. So, well, we will say that it is 1. Okay, I'll define h of 0 is equal to 1. The only sequence is you stay at the point 0 itself. Okay, so there's no moving up and down. That I'm calling a sequence. For n is equal to 1, it's a 2n length sequence. The only sequence that I'm allowed is this one, right? 1, -1. For n is equal to 2, I have a 4 length sequence. These are the only 2 allowed sequences that I have. 1, 2, 3, 4. Okay, so my axis is always going to be, so this is going to be 1, this is going to be 2. My bottom line is always going to be my x-axis, okay? 0, I'm not going to draw it. For n is equal to 3, now I have 6, right? There are a lot of sequences for this. Let's try to draw all of them. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. That's number 1. 1, 2, 3, 4, 5, 6. This is number 2. 1, 2, 3, 4, 5, 6. Then I have 1, 2, 3, 4, 5, 6. I'm counting wrong, but whatever. And the brother of the sequence, 1, 2, 3, 4, 5, 6. And last but not the least, 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Okay, and so I have a total of 5 sequences for this. And if this pattern is recognizable to you, 1, 1, 2, 5, also the fact that this section is on Catalan numbers should give you a hint that this is somehow related to Catalan numbers, and you would be correct. We have that Cn for n greater than or equal to 0, for n greater than or equal to 0, Cn is equal to number of permutations a1 to a2n of the multiset n times 1, n times -1, such that each partial sum is non-negative, such that each partial sum is non-negative, Okay, great. This is my theorem. Let us try to prove it. Proof. Well, what we are going to do is we are going to say, hey, look at all the sequences. Sn is equal to a set of all sequences, all permutations, and so by now you should know that cardinality of Sn is, well, the set has n ones and n minus ones. This is exactly equal to 2n choose n, because it suffices to choose the n places there where there are 1, and there are the other n places where there are -1s. Okay, let an be the set of permutations that have non-negative partial sums. Set of permutations with non-negative partial sums and want to show cardinality of an is then Cn. That is what we want to show. Let un be Sn minus an. I think I have used this notation before, but in case you don't remember, this means set minus. So from the bigger set Sn, you're removing all the elements of an, and whatever you get is Sn. Okay. Well, by lemma, suffices to show cardinality of un is equal to 2n choose n minus 1. Okay, because my lemma says, this, okay, yeah, since an plus un would be cardinality of Sn, right? You know the addition principle. I'm dividing my big set Sn into two sets, un and an. I want to show the cardinality of an is Cn. Well, that suffices to show cardinality of un is Sn minus Cn, which is exactly 2n choose n minus 1. Okay, how do I do this? Let me define another set. Let Tn is equal to set of all permutations, all permutations terms of the multiset n plus 1 times 1 and n minus 1 times 1. Okay, then it is easy to see cardinality of Tn is 2n choose n minus 1 is equal to 2n choose n plus 1, whatever floats your boat, choose that one. Okay, and so if I show there is a bijection, therefore suffices to show a bijection f from un to Tn, right? If there's a bijection, then both sets have the same cardinality, and so that means the cardinality of un is also exactly 2n choose n minus 1. Okay. Now, because I am looking at given, take a permutation a1 to an in un, then it has at least one non-negative partial sum. It has at least one non-negative partial sum, right? And the easy way to see this is S2, not an, that should be a2n. Well, the easy way to see this is S2n is always 0, right? If I'm taking n positives and n negatives, in the end, I am going to end up with 0. Okay. So pick the minimal k. Pick the minimal k such that sk is negative. Okay, so oops, I didn't mean to say non-negative, I meant negative partial sum. My bad. This has at least one negative partial sum because otherwise it would be in it would be in an, right? So it has at least one negative partial sum. I am going to call that partial sum as sk, right? So my sequence looks possibly something like wah 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 wah, and then -1. So this is going to be my sk in that case, sk. And this is because this is the first time that my sum is equal to -1. This is the k I want. Okay, observe. K is odd. Okay, k has to be odd, otherwise the sum, whenever the sum is whenever k is even, the sum is even, -1 is an odd number, you can't have that as the sum for an even number, right? sk minus 1 is equal to -1, and sk is -1, and sk minus 1 is actually 0, because this is the first time I am hitting a negative number, right? So it better be 0 for the previous one. It just could be that my first thing itself was a -1, but that's fine. That tells me that a k is actually -1, right? And the sequence a1, a2, dot 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 up to a k minus 1 has exactly k minus 1 over 2 ones and k minus 1 over 2 negative ones. Okay, that is going to be true because my partial sum is exactly 0. The number of ones has to be equal to the number of negative ones. They have to match up, right? Then what we do is make a new sequence, well, then instead of make a new sequence, map this sequence to -a1 -a2 dot 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 minus ak minus 1 minus ak, and then ak plus 1 to a2k left as they were. Okay, so now how many ones are there and how many negative ones are there? This new sequence, has, well, there are k minus 1 over 2 negative ones from 1 to k minus 1s. So when you flip all of that, it preserves the number of negative ones and ones. But you have flipped one extra negative 1. So you have k plus 1, well, not k plus 1, n plus 1 ones and n minus 1 negative ones, right? Because initially you had n and n. In 1 to ak minus 1, you flipped equal number of ones and negative ones, so you didn't change the balance there. But ak you flipped to change the balance, so now it has n plus 1 ones and n minus 1 negative ones. Therefore this sequence belongs to, therefore this sequence belongs to Tn, right? And therefore, I have a map. This gives a map. This gives a map from Un to Tn. Okay. It is easy to check that it is injective. It is actually injective just by construction. If you take if you take a sequence, find the first term where it is now positive, because this is a -1 to ak -1. All of the partial sums are going to be negative now, and then suddenly it becomes positive at ak plus 1. AK is the first time where your partial sum sequence is positive, right? So that's easy to see, and that also gives me an idea how to construct the negatives, construct the inverse map. So maybe I should say map f from Un to Tn. Okay. This is injective by construction. One to show surjective, one to show surjective. Okay. So let b1 ... b2n be a sequence in Tn, right? This sequence has n plus 1 ones and n minus 1 negative ones, right? So the total partial sum, therefore total partial sum is equal to 2, right? So what we want to do is, as I was saying when we created the map, when I'm inverting the first time that my partial sum is negative, that would be the first time my partial sum is positive. Pick k such that sk is equal to 1 for the first time. Such that sk is equal to 1 for the first time. Okay. Or the partial, which is equivalent to saying that the partial sum is positive. So b1 plus b2 plus ... plus bk is equal to 1. That, and because it is the first time that this sequence is positive, and bk is equal to 1. Because otherwise, if bk was negative 1, then the sum would have been... Okay, let me change it so that this statement literally says it is positive, whatever. Such that the partial sum is such that kth partial sum is greater than 0 for the first time. Okay. So we have this. Then there are, in b1 to bk, there are k minus 1 over 2 ones and k minus 1 over 2 negative ones, and you get the sequence. Therefore, construct sequence AI is equal to minus bi if 1 smaller than or equal to I smaller than or equal to k, bi if k plus 1 is smaller than or equal to I smaller than or equal to 2n, right? So invert everything, before k, or before or equal to k, and leave everything afterwards same, then a1 dot 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 a to n belongs to un, because now the partial sum was 1. When you flip it around, the partial sum is -1, and it is and this is the first time it is the partial sum is -1, and f of a1 a to n is equal to b1 b to n. Therefore, f is a bijection, f is surjective, f is surjective, surjective. Therefore, f is bijective, bijective. Therefore, cardinality of un is equal to 2n choose n minus 1. Therefore, cardinality of an is cardinality of Sn minus cardinality of un is equal to 2n choose n minus 2n choose n minus 1, which is equal to my Catalan number as we wanted. Okay, I'm going to stop this video here. We'll look at some more in the next video.